This is 2160, lecture 8, continuous time Kalman filter. So just a quick recap what we discussed last Monday. So this is the just a overview of a discrete Kalman filter. So up to time t minus 1, we got the some state estimate, the x hat t minus 1. And then this one is to be updated to xt hat at the time t equal t after receiving the actual measurement yt. But before going there, we have two steps involved. First step is so-called the propagation. Xt minus 1 hat is propagated to next time step xt conditioned by t minus 1 state. It's called a priori state in the sense that this is before we acquire new sensor and information. Now to make a comparison with this, we have to create the predicted output, the sensor output based on the output measurement equation, and then make a comparison, and the error is used for updating the state. It's called the update state, update process. And updated state is called a posteriori state after we acquire, this measurements. So two processes, propagation and update, are repeated recursively. So this is just a summary. This is recursive formula. So you need to provide the initial conditions and x naught for initial state and a p1 / naught at initial values of the a priori error covariance. So state and propagation, so we basically make the comparison between the measured and then predicted based on these equations, and actually multiplied by this Kalman Gain KT and update this, right? And then KT, Kalman Gain, is given by this lengthy expressions where PT t minus 1 is involved, and that is actually computed on the right-hand side. And starting with the initial conditions, we can immediately find the t equal 1, P1. And with the P1, we can actually compute the P2 / 1. And then hereafter, we can continue the recursively compute all P's. That is actually to provide the Kalman Gain KT, right? So that's actually the algorithms. Now, I have a couple of important points which we did not discuss the last time, but it turns out to be important. One is the so-called innovation covariance. The key part is we predicted the output in yt hat, and then this one is compared against the actual measurement to y, right? So, it may be useful to consider the covariance of this output error, which is called innovation covariance. And the definition is yt hat minus y, that is actually, output error, right? And we place these, back to back to create the covariance matrix. And then this one, interestingly, is involved in the Kalman Gain. This ST is given by this part, which is basically the Kalman Gain's, inverse part, okay, this part. So let's actually prove this. Let's prove this expression. The ST, by definition, it's actually given by this. So let's replace y by yt, ht, xt plus b, right? So I put it in here. And then y hat is basically a prediction based on the this a priori state. So xt t minus 1 and hat, okay? And here we see, factoring out the ht, we can actually find the difference between a priori state x hat t minus 1 minus xt, which is actually by definition, it is a priori error variables, epsilon t minus 1. Okay, so we have epsilon t minus 1 h minus vt, and then expanding this, we get the four terms, but in cross terms, epsilon tt minus 1 to vt, if you take the expectation, meaning that the correlation between epsilon tt minus 1 and the vt, that turns out to be 0, as we proved in the last time. So, by expanding this, all you have is ht, expectation epsilon tt minus 1, a priori, error. This part is a VT-VT transpose, which is actually, by definition, it's actually, sensor, covariance, error covariance, RT. And this part, this is in the definitions of PT to T minus 1 is given by this. So, the bottom line is that, if you compute this output error covariance, you arrive at this expression, which is involved in the Kalman filter sitting here and the inverse term, as you can see here. All right, so this is the Kalman filters, and this particular part is innovation covariance inverse. Okay. Now, we like to do a little bit more physical interpretation of the Kalman Gain. And this is the second point today. So Kalman Gain is given by this equation. And this particular part is innovation matrix, innovation covariance, inverse, right? So let's multiply this innovation covariance to both sides to clear the right-hand side. And you get to this expression. And then now we use the covariance update law. Remember, PT T minus 1 is basically attenuated, reduced by incorporating the new sensor measurement, right? Which is to reduce this by this much. Yeah, so let's use this equations. And PT T minus 1 is now first distributed to two terms. And this product is to be moved to the left-hand side. You get this equation, and we push the PT to the other side. So this, matrix product equal PT T minus 1 minus PT. So looking at this expression coming from the Kalman Gain, KT, HT, PT minus 1 is the one here exactly. So this product is replaced by PTT minus 1 minus PT. So that is this expression, PTT minus 1 PT. Don't forget to put the HT transpose here. And the KT is multiplied to RT, which is sitting here, right? This is equal this guy. Now, by distributing this, easily you can find this one, and the right-hand side of this is canceled. So the rest of the part is this guy. And solving this for KT, Kalman Gain KT equal a posteriori error covariance PT, and output the measurement equation matrix HT, and then sensor noise covariance inverse, right? So I know this simpler expression may be easier for real interpretation of the Kalman Gain. So Kalman Gain is proportional to the inverse of the measurement noise covariance RT inverse, and then also proportional to PT, that's a posteriori prediction error covariance. So what this means is that if you have a very horrible sensors, okay, very inaccurate sensors. Like last night presidential debate, someone made a very inaccurate statement. Suppose you get that kind of information, you take it with a grain of salt, right? So you basically reduce the Kalman Gain, because if RT is big, this one is reduced. That makes sense. On the other hand, if the posteriori error covariance PT is large, what that means? We don't have a good confidence with the current prediction, right? So what you do, you now get the new data, you jump on, right? That's exactly what you need. So, you're more, geared towards the that actually new observation. So KT is increased as the PT is actually, on the larger. Make sense? So that's actually, the interpretation of Kalman filter sounds very similar to the previous, recursive least squares estimate. You get the some recursive formulations, right? Very similar things are happening over here. But major difference is that the Kalman filter, we quantify noise. So here, RT is involved. We quantify the accuracy of the sensor, and then we, accordingly, we attenuate the gain. Okay, cool. So that's all about the discrete time Kalman filter. And what we like to do is to extend it to a continuous time Kalman filter. So that we deal with the linear time varying system. So this side is all discrete time, and this side is continuous time. We use a slightly different notation. Instead of this difference equation, we have a differential equation. And A sub t is now replaced by F t, and then xt is replaced by x of t. Okay. Yeah, what we like to do is actually find the continuous time version of Kalman filter by extending this discrete time, and then and it is conceivable that this state update law is now extended to this instead of this subscript t. We have the derivative, time derivatives, and then that's actually basically copying this part and putting it here, and then we have this error state correction terms, which is the same one as this, making the difference between the actual measurement and the predicted one, and multiplied by some gain KT, that is added to this, the same form. Now, one big difference is this. It's basically covariance update and covariance propagation. Interestingly, we had two formula, covariance update and covariance propagation, right? These two, as we actually put the delta t, that's the time interval, sampling interval, reduced to 0, these two collapse, and then it becomes one differential equation named the Riccati differential equation. This is actually a very, in a sense, a succinct representation of the evolutions of error covariance P, and also it is actually a useful tool to better understand the basically the analysis of the Kalman filter, how it behaves, and so forth. Yeah, the more rigorous actual treatment, addressing the relationship between discrete time and continuous time could be done based on the more rigorous so-called stochastic differential equations. This is actually stochastic differential equations. But in today's lecture, we just take a little shortcut because that is not our interest. And then after we have the Riccati differential equations, we have more interesting things to do. So let me just take a little bit shortcut here, and then we use just a standard relationship approximating the time derivatives with this actually simple formula. Okay. Now, so state equations, x dot is now replaced, approximated by this xt plus 1 minus xt over delta t, and just multiplying the delta t both sides and move the xt to the right hand side, you can write this equation, right? And you can compare this one to just a standard discrete time state equation, and you find that this part is to be AT, and this one is GT, and then WT. Okay, now a little bit more tricky part is actually a modeling of noise. And between continuous time and the discrete time, some significant difference exists. So let's look at that. So in the case of a process noise, WT is fed into the systems, and in the case of a continuous time, you have an integrator. X dot T is integrated to get the XT, and then you have a feedback through AT, and that's actually what this state equation says, right? This state equations say the WT is brought in, and then that goes to basically integration to move to next XT. So that we have it, okay? So the WT is fed in, and it goes through integral part, and then arrive at the some XT. On the other hand, on discrete time, because of the internet disruption, this is just a recording of lecture number 8, but I hope you can get it. The topic is a continuous time Kalman filter. I'm going to explain this from the beginning, even though many of you attended the first 10 minutes of talk. So this is the quick recap. Suppose we have estimate at the time t minus 1 with this hat over here, and then we'd like to update this estimate to xt hat by assimilating new data on the yt. We have 2 steps. One is a propagation, the other is an update. The propagation, we basically predict the expected output sensor signals through simulations and the internal model, and we create the predicted one, yt hat, which is compared to the assimilated real sensor data yt, and the difference is used for correcting or updating the state xt t minus 1. Before this assimilating the signals, we basically predict the output, a state, which is called the a priori state, xt / or conditioned by t minus 1. And after getting the data, it's called the a posteriori state. And then this process is called the update. And since Kalman filter is a recursive formula, you need to provide initial condition for state x0, starting with this. You predict the output, and then the output is compared with the actual sensor signals, and then state is updated to this value. And here we use the Kalman Gain KT. It is given by this expression, and the key part is PTT minus 1, a priori error covariance. That is actually computed on this side, starting with the initial a priori error covariance P1/0. We can immediately compute the P1 based on this covariance update, and then actually covariance propagation algorithms comes in to compute P/2/1. And actually repeating this, we can compute all P's, thereby we can provide all Kalman gains necessary for computing this. Now I have 2 important points to add to the Monday's lecture, and one is innovation covariance. We did a prediction output in yt hat compared to actual measurement y, right? So it is conceivable to actually look at the covariance associated with this output error, which is called innovation covariance. The definition is this: yt hat prediction minus true measurement y, and then we put the back-to-back to create the L by L matrix. This is innovation covariance. Now, this innovation covariance matrix is heavily involved in the Kalman gain. In here, ST inverse sitting here. And then this is the one that, we saw here. KT is given by this, right? So inside of this is actually innovation covariance. So let's actually look at the that relationship, whether that is correct. So what we like to do is to prove this one, ST, defined by this, is basically given by this, related to this expression. So ST by definition, given this, let's replace Y by HT plus VT. This is the output equations, right? So sitting here. And YT hat is basically given by the prediction, which is based on this XT minus 1. And if you can, as you can see here, if we factor out the HT, you get the difference between XT minus 1 and XT. That's nothing but this a priori error. So let's put this one into here, say, then we simplify this. Now, next one is to distribute this and compute the whole expression. Now, in doing so, we have the terms, close term between epsilon TT minus 1 and the VT. But as we examined last Monday, the correlation between epsilon TT minus 1 and the VT is basically 0. So using that, we get only two terms here, sitting here and here. One is epsilon TT minus 1 back to back here, which is basically a priori error covariance PTT minus 1. And this one, VT transpose, this is actually the definitions of the error covariance matrix of the sensors, RT. So we arrive at this way, so this is correct. So Kalman gain can be expressed by using this innovation matrix. Now, next, I'd like to do a little bit more physical understanding or interpretation of Kalman gain. So Kalman gain in this form is a little bit complex, so we can rewrite this in a more convenient form. So shown here is that this particular part is innovation covariance. So let's first multiply this from the right side, post multiply that, you get this expression, right? Now, we'd like to introduce the other expression that's basically covariance update law. PT equaled I minus KT times the PTT minus 1. So before assimilating the data measurement, we generally had a larger error covariance, PTT minus 1. But with the incorporating a new measurement, which is actually through a Kalman gain KT, we attenuate this one from this value to this value. And this is the matrix multiplied, right? So let's use this expression. So first, the PTT minus 1 is distributed to these two terms, and this product is moved to the left-hand side, and the PT is moved to the other side. Then you get this expression. Now, if you look at the this line, KT, HT, PT minus T minus 1, exactly the same one, this particular part can be replaced by this, right? So putting this one here, PTT minus 1 minus PT, and then HT transpose, and then actually this one multiplies to KT, and the rest of the part is this one. So now distributing this one to these two terms, the first term here, shown up here, is exactly the right-hand side, so these two cancel out, leaving this two terms from which we can solve for KT, that's a Kalman gain. So Kalman gain KT equal PT HT transpose RT inverse. RT is assumed to be positive definite and non-singular, right? So Kalman gain is proportional to the inverse of the measurement noise covariance R inverse, and also proportional to the posteriori prediction error covariance PT. So what that means? Well, we can do the following interpretation. So if the sensor is not accurate, okay? Like the last night presidential debate, someone said all kind of inaccurate statement. So if you hear that kind of inaccurate sensor signals, you take it with a grain of salt, right? So we attenuate the Kalman gain KT, which is to lower the correction that you make, right? If there's a very reliable sensor, reliable information, you take it more, right? How about this PT? PT represent the a posteriori error covariance, state estimation error covariance. If this one is big, that means that we don't have any confidence with the current situations, right? Now you got the new measurement. You really want to use that, so we jump on that, right? So the less we have a confidence, in other words, we have a larger error covariance, PT, we actually make the large change with the large Kalman gain. So this kind of interpretations are very similar to the one we had for recursive least squares. Only the biggest difference is that here we quantify the noise characteristics. So RT is involved. Recursive least squares, we did not actually quantify the error and properties. So we didn't have that at that time. With that, we'd like to go to the continuous Kalman filter, but this here is actually the comparison between discrete time Kalman filter and then continuous time Kalman filter. Excuse me. So now discrete time, this is actually state equations, state transitions, or difference equation. Now this part is now replaced by differential equation for continuous time. And then we use a slightly different notation. Again, the BT, UT is actually ignored in here. I didn't put it in here, but that's actually deterministic part. It's not essential for this prediction problem. YT is actually extended to this form in the same way. Now, this is the state update with the Kalman gain KT, and here is basically open loop simulation, and then actually propagation is made in here, right? So here too, and we just cut and paste this part, and then right here, this is similar to this equations, and then we just propagate the XT with this FT. In addition, we have this correction to the state, okay? Now, in the case of discrete time Kalman filter, we had two formula for covariance update and covariance propagation. Now we had the two different formula here and here, but now as you reduce the sampling time interval delta t smaller and smaller, these two expressions collapse and combined to a single equation, and then that becomes a differential equation named Riccati differential equation. Now, extension from here to here, or reduction of this one continuous time to a discrete time, we can do a more rigorous treatment based on statistical differential equations, but that's actually a little bit lengthy expressions process, and that's not our main interest. So today, we just use a simple reduction using the standard approximation of time derivatives by this expression. So starting with the state equations, I just replace the time derivative of state by this, and then multiplying the delta t to both sides, and then moving xt to right-hand side, you get this expression. If you look at this, this one is basically corresponding to AT in the discrete time state equations, and then the GT and the WT corresponds to this in this way. Now, that's simple. However, one tricky thing that we have to pay attention to is the modeling of noise. excuse me. So in the case of continuous time, and the noise Wt comes in, and it has to go to this integral part. This is clear if you look at the state equation here. Wt is fed in, and then actually, derivatives there, so that means actually, x is actually integral of Wt. Therefore, when you look at the this diagram compared to discrete time, you have to take into account the difference, because in discrete time there's no such integral part in here. This is just a one step time delay. So when you actually make a comparison between the two, Wt in this sense, having no integral here, is basically corresponding to Wt that goes through this integral result in the xt, right? So Wt in discrete time can be considered as actually integral of the w/tau d tau integration for the period of delta t. And then let's say in the average value of this shorter time delta t, w is this guy, and then this can be written in this way. On the other hand, the measurement of noise doesn't have that kind of difference, just added to this one, right? So Vt, what this means is that this can be treated as just a time average of a Vt for actually shorter time period, the delta t. So what I did here is actually, this is actually an expression for obtaining the time average of that Vt over delta t, and then which is written at the V, upper bar t. Now, the question is that how that the difference influences the noise covariance. So in the case of the Vt, which is actually measurement the noise and a measurement of noise, and actually continuous time and the discrete time are related in this way. So based on this, let's compute the covariance RT. The definition is Vt transpose back to back, and we substitute this expression into this. One tricky part is integration is involved, but this integration is inside of this computation Vt, and then the same Vt, however, inside of it, it should use different integral variables. So I use a tau prime as opposed to tau. So two integrals is involved. So first part, let's look at these situations, and we're putting the expectation inside. We basically, get this expression, E V tau, B transpose tau prime, okay? And then we integrate this, for the interval to delta t. So to this particular part, by definition, we had, the zero, covariance when the tau and the tau primes are different. And actually, it takes the matrix R tau when tau equal tau prime, right? This can be conveniently written by using Dirac's delta function, which is actually say that t equal and tau equal to tau prime at that particular instant alone. The delta t is to take that value of 1, and then that represents this area. Okay, this area is to be 1. So, computing this inside of this first integral loop over here, this one can be reduced to, because, even though we change this, only the instance of tau equal tau prime takes the non-zero value. So that actually becomes R tau when actually, tau equal tau prime. The rest of the part is, outside the integral that, remains here. And actually, this is basically we use the average operations. So it is given by R bar T over delta T, because the delta T squares over here, and then this cancel out, resulting in this expression. We can do the same operations for QT, but remember that the Q related to the process noise WT, and then W continuous time T are related in this way. Delta T is actually sitting here. Therefore, the result is different, and the Q bar T equal 1 over delta T of this guy, okay? As opposed to this one, RT is this, okay? So that's actually a significant difference between the two. So to summarize this, we have AT correspond to I plus FT times delta T, and H basically the same, and RT turns out the R bar T over delta T, and then QT it times the delta T, okay? So therefore, the Kalman gain can be expressed in the following way. We got this expression, right? RT inverse, and then here's the a posteriori error covariance. So I know these are basically this one is replaced by this expression, and this one too. So the KT is actually corresponding to this expression. So difference between Kalman gain in the discrete time and the continuous time is that the delta T must be multiplied to KT. Now, covariance propagation and covariance update laws can be combined. We use this one a little bit later, but then let me just first show this. So I know this is the error covariance propagation law, right? We know it. Now, PT is basically, I minus KT, PT, T minus 1. So I just substitute this one into this. This is to show directly the transition from a priori error covariance PT T minus 1 to PT plus 1T, one time step ahead through this stuff. So the main part is actually combining the covariance propagation law with the covariance update law. What the sort of expression coming out? Okay, now we now know that these stuff and the plus KT. So let's substitute these into this expression. See what happens. So following this expression. AT is basically I plus FT delta T, right? So let's replace this guy by this expression. And 1 minus KTHT, KT is now extended to, KT is now replaced by KT delta T. So let's actually replace this one by that will result in delta T, KT, HT, okay? And then just to put this one here, and then lastly, this one again expanded to this with the transpose, right? And then this QT is actually Q continuous time T and the delta T. That is an expression that we have obtained over here. So what we like to do is first expand this. And this includes delta T, and then some of the cross product here, delta T square, and cross product of this, and this may include the delta T cubic, right? Cube. But those higher order delta T's, small quantities are all putting here. And let's focus on the first order delta T, and then actually constant terms. So starting with this, expansion, if I take I, and then I over here, and then the PT T minus 1, and the I, that's resulting in PT T minus 1. If I take F delta T and I, And actually, I over here, that result in delta t ft from here, and then a pt t minus 1 over here, and then I, that's nothing. Okay, so we just collect the terms having only single delta t. So the next, let me just explain this I times this guy minus delta t, kt, pt, and then pt minus 1, and I take this I, and then we got the expression, like, and then lastly, I, and then this one result in this. And all the other combinations, when you expand this, are involved in the higher order small quantities. Well, now I have to include this guy over here too. Okay. Now, interesting point is the following. So, yeah, what we like to do is basically, this is the, the end result of the previous slide, right? So, first of all, we like to move PTT minus 1 to left-hand side, okay? And then divide both sides by delta t. So to create this expression, and the remaining part is here divided by delta t, and then we ignore higher order small quantities. You end up with this expression. And then now what we like to do is to push delta t to its limit to 0. And obviously this one becomes the derivatives of p, right? Now, as you actually reduce delta t, a priori, covariance, and then a posteriori covariance, getting closer and closer. And then we assume they are actually converging to the same one. And then that is given by the Dix expression. And then now we represent it as a continuous time covariance matrix PT. So when we do this, what the sort of equation comes out? Yeah, so this is the full derivations. So we did up to this point. So this left-hand side becomes the time derivatives of PT, right? And here it's actually replaced by PT. Then this one replaced by PT and the F transpose, right? Here I use the KT as a PT, HT, R inverse sitting here, and then actually combining this, this term is obtained, and then this one result in this. So this is actually a differential equation that is actually to determine PT. In the discrete time, we followed two steps, covariance propagation and covariance update. Now these two are combined together, and then we have this, one differential equation that actually subsume two steps into just one. Now, well, at the final stage, I just replace the KT by this expression because our objective is to obtain KT. So, we don't know the KT. So, if you just leave this one as it is, we can't actually solve this because, chicken and egg problem, we don't know KT, right? Rather, replace this one by this, leaving this equation only the variables of PT, and others are known parameters. Only PT is unknown. That's actually, we like to solve for by using this differential equations. So once we determine PT, back that one into this, we can actually construct the Kalman Gain KT. So this differential equation is very important, governing equation to determine the basically, Kalman Gain. It's called the Riccati differential equation. The Kalman Gain is determined from a solution to this equation. Now, several important notes you should pay attention to. First of all, it is actually, PT is basically a matrix. So this one is not the scalar equations, but matrix differential equations. So, this one is actually PT is n by n. It's actually by definition it's a symmetric matrix, and it has 1 over 2 n times n plus 1 independent scalar differential equations are all involved in this expression. Now, this Riccati differential equations has a very clear physical sense. So let's examine that. So it consists of 3 lengthy terms, right? So dp dt, first group, basically ft pt plus pt and f transpose. This one and f is involved. F is governing this, so f is coming from f came from the state equation. So f is determined how the state make a transition, right, by itself. So this term ftpt plus pt f transpose. This is represent the effect of the unforced system dynamics upon the error covariance transition. Unforced means that we look at these equations, and this one is basically driving the systems. So without this, the remaining part is this. That's actually unforced dynamics. The systems are more inherent characteristics, right? So PT is having a summer value that is actually, value make a transition in this way. If the system is actually stable, this one may be converging, right? If the system is unstable, this one is making actually bigger and bigger, could actually, diverge in some sense. So that is determined by these 2 terms, okay? Second terms and the third term. Second term, well, if you look at this and the length expression, but easily you can find that this one is actually a symmetric matrix, right? Symmetric. Plus, you can also easily prove that this matrix is at least positive semi-definite, right? You know how to prove that, right? So yeah, this one is positive, but that with this negative values, this tend to reduce the PT, okay? Tends to reduce the PT. Expected reduction of uncertainty, okay? Basically, PT is an error covariance, so this is to show the levels of uncertainty. Expected reduction of uncertainty as a result of state update using the sensor signals. That the sensor has error covariance and R. Okay, and the last term, this is also a positive semi-definite matrix with the plus sign. So this is to indicate the expected increase of uncertainty due to process and noise with the QT. So as it is to propagate, it is to face the system's process noise, which is characterized by QT. Okay, so this Riccati equation is a key component to determining the optimum, state, update gain, that's Kalman gain KT. It aggregates both the state propagation and the state, update laws, and represent how each of the propagation and update contributes to the prediction uncertainty. Together with the inherent dynamics of the process. Okay, so this is just a quick summary of a continuous time Kalman filter, or it is called Kalman-Busse filter. Busse is a Kalman's collaborator, co-worker, and also to some extent, actually, senior co-worker or boss. Yeah, the vintage in 1961. So we deal with the linear time varying systems given by this equation. And then we assume that the system is observable. So matrix FT and HT, this pair, is assumed to be observable pair. And the noise V and the W are uncorrelated. This is just direct extensions of the noise properties we use for discrete time. Okay, Now, state transition Kalman filter is given by this with the Kalman gain that is given by this, and the Kalman gain, includes PT, and error covariance is governed by this Riccati differential equation. So that's actually continuous time Kalman filter. So now what we'd like to do is to better understand this, continuous time Kalman filter. So let's start with the algebraic Riccati equations. At the end of the day, we'd like to better understand how this Riccati differential equation behaves. How the PT, that's actually error covariance, evolves with the time, and our concern is that would that be converging? If it's converging, where it's really converging? Is it converging to 0? Which is very actually desirable case. A prediction error is to be 0. That's great, but under certain conditions that may not be the case. So time pushed to infinity. What is actually this value, infinite value? So before analyzing the dynamic transition, which is governed by the Riccati equation, but a Riccati equation is a matrix, and the Riccati equation is more important. It's a nonlinear because the PT, sandwich from both sides, it's basically nonlinear dynamic equations, and that's not easy to solve. So to begin with, we'd like to actually look at the steady state problem. So first, we assume that the matrix Riccati equation, differential equation, converges to some point. Let me denote it that P infinite, P sub infinite is the it's actually a steady state value, and in some way at the steady state actually time derivative of PT is basically winding down to 0, right? And then these parameter matrices are going to some constant. So original Riccati differential equation is now reduced to the following algebraic equation by setting this ddt pt to be 0. It becomes a algebraic equation, even though it is actually nonlinear, but much simpler because it's algebraic. So this is called the algebraic Riccati equation, or ARE. So, to better understand this, it's still a matrix a little bit complex. So let me start with the scalar case, okay? So all the F and P's are all just a scalar quantity. So we can actually simplify this one into this form. H is also a scalar, so we can write it to H square, and transpose, or it doesn't matter, it's just a H, scalar quantity. So we can write in this way. So this one is quadratic equations, second order algebraic equations, because the P square is involved here. But this one is, we can solve it directly, and then P infinite is given by this expression. We do have two solutions, plus and minus. And here's the things, which one to take? Remember, by definition, PT is always actually, positive, at least positive, semi-definite, right? So that said that, we can't take the, negative value, because, if you take the negative sign, this actually magnitude is bigger than F, so that's bad. So we must take the positive part alone. So this is solution. Okay, so now let's actually examine the properties of these solutions. Okay, so P infinite is given by this. We have no idea, so why did this one actually coming out in this way? So let's look at the special cases. First one is this state transition equations matrix. Now the scalar F is 0. Okay, so if F equals 0, AT equals identity matrix. So F equals 0, this one collapses to this equation, which is simple. Now our interest is under what conditions this actually prediction error covariance goes to zero, basically a zero error. Okay, so at the steady state, this guy is to be usually non-zero, right? And as we have a higher value of R, higher value of Q, it is to be higher. This makes sense. Higher value of R means that your sensor has more noise, and the noise variance is higher. And the Q is also the magnitude of your process noise. And as you have a higher value of Q, you get the worst result in terms of the state estimation error, right? Now, interesting case here is that since we assume in this case F equals 0, F equals 0 means that, well, it is actually the case that the same value is transmitted to the next one. The state doesn't change. So that is actually the case that the estimating some constant parameter value. Constant parameter value F equals 0. We discuss it more in the example later, but I know constant value is 0, and if you have no disturbance to that constant parameter estimation, both F and the Q are 0, then this becomes 0. So that's one scenario. Estimating some constant parameter, we expect the 0 estimation error covariance. The other situations is that the Q may be 0. Okay, you have no process noise in there. So reducing and eliminating this Q, you end up with this equation: F plus square root of F squared. Okay, you must be careful in treating this, because if F is positive, then this one comes out, so it turns out to 2 times F, right? 2 times F. What does this mean, F positive? F positive basically the system is unstable. Okay, if the system is unstable, even though process noise is not coming in, but you end up with the non-zero steady state error covariance. So you can't estimate that perfectly if the system is unstable. Okay. On the other hand, if F is negative, what happens? F squared is positive, and square root of this one is to give you the positive value as a whole, and then F is negative at this time, so these two cancel out. So that means that P infinite is 0. So this is interesting. If the system is stable and actually having no process noise, P infinite going to 0. Okay, this is one lucky case. If the system is stable and no process noise, then actually at the end of the day, you get the perfect measurement. Now, so as far as actually this sensor noise side is concerned, R can't be actually a negative or 0, perfectly 0. But I know some good sensor R is extremely small, so that's actually going very close to this. Okay, but anyway, covariance matrix P never goes to 0 unless F actually stable or marginally stable, and Q equals 0, no process noise, or you have almost perfect sensors to use. Okay, up to this point is actually algebraic Riccati equations. Maybe I should recap these things a little bit. So where we are, so we basically spend some time to characterize the covariance, the noise. But main point is that we actually reduce the propagation law and update law of covariance into one equations. In doing so, we putting together, and at the end, we actually arrive at this Riccati equation. Maybe I should just show this. Yeah, this one. So this may be the summary. Okay, so this is almost the same, and it is still combined. We got the Riccati differential equations. So and with this we consider the physical sense, and it's actually going to governed by the original plant dynamics and expected reduction by actually incorporating a new sensor signals. Covariance gets smaller, and actually process noise is to increase the covariance. So perhaps you remember that in a discrete time, the covariance basically go up and down, up and down. Remember that? Going up when you propagate and going down when you update, right? Now, in the case of continuous time situations, these two actually zigzag stuff is actually reduced to just a smooth curve like this, and no up and down involved, just smooth curve, but it's a governed by many factors. Even in the case of a scalar case, we included both state properties F and actually two noise source properties, R and Q, sensor noise and process noise. Both plays a very important role. So that's actually all about up to this point. Okay, now I'd like to move on to a little bit more actually challenging, mathematically intense materials. That's actually, we'd like to solve the Riccati equations, Riccati differential equations. So we have examined the steady state solution to algebraic Riccati equations. And however, the original matrix Riccati differential equation is basically nonlinear, and then it's a matrix of simultaneous equations. The behavior may be very tricky, right? So here we examine the transient response of the differential equations and discuss the conditions for obtaining physically meaningful solutions. So that's a very important part. So we introduce a technique for solving the matrix Riccati differential equation named the matrix fraction decomposition. This is a beautiful technique, but it's a little bit involved. So, okay. So now suppose that the square matrix PT in the matrix Riccati differential equation is somehow decomposed to PT equal 2 matrix AT times B inverse T for all T, okay? So I know this must be well defined. The AT and BT must have the consistent dimensions. And actually, the BT is actually non-singular all the time, okay? So if you just replace, decompose this for PT into these two, AT and the BT is actually two matrices that we like to obtain for actually constructing PT. Now, interesting point is that the AT, BT can be obtained. Basically, the original matrix Riccati differential equation can be rewritten, can be transformed to the following matrix equations, which is linear. So AT-BT DDT equal some complex matrix times AT-BT. This matrix, and later we call this this is a type of Hamiltonian matrix. So, that original Riccati differential equation can be reduced to this linear form. So how it works? This is actually a lemma. So we start with the matrix B, which is actually assumed to be non-singular, right? So BT, B inverse is I. Let's differentiate both sides. First, this is the product of these two terms. So differentiate one, one by one. So differentiate this times this B dot the B inverse, and then this differentiation comes with the B, and dot equals 0, right? So we can solve this one for B dot inverse, and the B is actually assumed to be non-singular, so we can write it this way. Okay, so now the trick is the following. First, so this is our definitions of A and B, right? So let's first take the derivatives of this. This is now expanded to dp dt equal A dot B inverse, and then AB dot inverse, right? And then the B dot inverse is now replaced by this, so it can be written in this way. Okay, A, and here it's actually minus times this guy, right? Okay, now this is one equation. The other equation is, we know this is our definition. PT is now expressed by this. So let's substitute this one into the original Riccati differential equation. So Riccati differential equations, sitting here, I just, for the convenience, I just wrote in. So FT and then PT is now replaced by A, B inverse. Let's put in here. And then again, AB inverse, and then times the FT, right? So here we have a PT in the two places. So first one, it becomes AB inverse, then H transpose, and R inverse H, and then again P, AB inverse. And then that's about the GQ, G transpose. Okay, now, so we got the two expressions for dp dt. One is actually this in equation 74, and then 75. Okay, so we can equate the right-hand side. That result in this expression. Okay, now we make the following trick. So, looking at the right-hand side, yeah, we basically, well, first we post multiply B to both sides. So this one goes out, just a dot, and then this one goes out, something times B dot equals going out, and then we put this one here and as such. Okay, now interesting trick is, so this is the last line. Now we basically factor out AB inverse from the right hand side, because here we have AB inverse, right, on the left hand side. So from right hand side too, we factor out the AB inverse in here. So two terms are combined here, right? So this one has no AB inverse. So here's the trick. Let's relate dA dt to this, and then dB dt to this one. Okay, both are having an AB inverse over here. So let's try to solve these two equations. dA dt equal FA plus GQG transpose B. And the dB dt equal H transpose R minus H and A, and then F transpose B. Okay, so interestingly, these two equations are basically linear in terms of A and B. They are basically simultaneous equations, right? So we can rearrange this into this matrix form. So here, dA dt, this first line, going this way, this times this, right? So ft times at sitting here, and then the next one, this times this, sitting here, right? dB dt, the second line, dB dt, this guy times A, here we go. And then this one, F minus F transpose B, right here, sitting here. So, these two equations can be combined and written in this single differential equation, which is linear. The matrix of the above linear differential equations, this particular matrix plays a major role. It's called, this is a Hamiltonian matrix. Okay, So the punchline, what is it? Well, why we care this? The punchline is interesting. If we find AT and BT, okay, by solving this actually linear differential equation, okay, satisfy the above linear differential equation, using that A and B, we can construct a PT. This PT is a solution to the Riccati differential equation. So because, A and B was created through this process, I just push a slide backward. You remember that the PT, A is given by A, B inverse, is actually, plugged into Riccati differential equations, and then we got this equations, right? So, actually, properties of A and B, which is give, and then this one, combining these two, we arrive at the this linear simultaneous equations with respect to matrices A and B. So once we solve this, plug in that one to construct the PTA times the B inverse, this guy is to satisfy the original Riccati differential equations. Then that's actually neat because the original Riccati differential equation is nonlinear, but we can solve this one by using the linear differential equations, and we get the same solutions. That is to the solutions of linear differential, Riccati differential equations. Okay, that said, it's still a little bit complicated. So again, we start with the scalar case. So A matrix, B matrix, both are scalar quantity AB. Let's look at this situation, okay? So, and the B is not actually 0, right? So we can actually rewrite and simplify the Hamiltonian matrix and differentiation in this way. So this is actually constant. Actually, we assumed all these are constant scalar. So putting this one here. So, I hope everyone can solve this linear differential equations. Well, you can apply any method, but let me just use this technique. So first, we compute the eigenvalues of this Hamiltonian matrix that gives you this expression. Yeah, we have two, eigenvalues, and then one positive, one negative. Let me just denote it. And the magnitude is lambda, and then two eigenvalues are plus minus lambda. Okay, and you can use any method to solve this, linear differential equations, and then end result of this guy shown here. But let me just use something. If you have taken the 2151 or some state space, method, you know how to solve the differential equations, given by this equations, and setting this one, replace this matrix as M. I wish to use a matrix H, but H has been used here. So let me just denote this matrix, Hamiltonian matrix, to be M. If this is M, the solution can be written this. Here, this part is actually, variable A's initial value, which is set to be P naught, and then variable B's initial value, which is actually set to be 0. So this is to show the initial conditions, initial state. Through this state transition, you arrive at time t equal t, you arrive at the A and B, in this expression. And M is that the Hamiltonian matrix, okay? And you have to provide the two initial conditions. And this initial condition is clever because, P equal A divided by B, right? And the B is set to be 1, so and A is to indicate that, and that the P value. So this is a clever way of doing this. So, yeah, this, from here, use that Hamiltonian matrix, we can, and now we have eigenvalues, so we can do diagonalizations or eigen decomposition, and V1, V2 are basically eigenvectors associated with the lambda 1, lambda 2. So we can put this one into this, and then distribute the exponential to this form. So yeah, and a solution can be given by this, and then rewriting this, and we can get the 18BT. So anyway, I know, I just use the Q as replaced to this guy, okay? So now we have a solution to that linear equation, to this one and this one. It's basically second, two second order differential equations, and two eigenvalues, and a magnitude the same as the lambda. So that can be combined in this way. So putting this A and B and upstairs and the downstairs, so you can get this. This is the the final equations. Okay, now, yeah, just for sanitary check, let's actually look at the final value as t tends to infinity, where this one is going. Lambda is actually positive. So E raised to the power of the -2 lambda t, as t goes to infinity, this one goes to 0, right? This is 0, and this one 0. So divided by this, actually, you end up with just a q over lambda minus f. And then you remember we did this replacement, and we have computed the lambda. So it turns out that this quantity is actually expressed by this. What is this? This one is exactly the solution to the algebraic Riccati equations. So let me show you that. Algebraic Riccati equations that we obtained right here. So P inverse, P infinite equaled R over H squared, blah, blah, blah. This is basically the same equation we have arrived at right here. Okay, this is just a sanitary check. So, we can actually compute the transitions of this new covariance PT. And for a given some parameter values that are like this, we can plot the transitions of P, starting with the somewhere here. It converges to this particular value at the end. I don't know what the values, and this looks like a 1 by combining these parameters into that and basically going to that value. So all these actually converging to the same actually point. Okay. Regardless the initial conditions, as far as the initial conditions starting somewhere here, it all converges to this. However, if you provide the initial condition that's actually lower than -1, it shows a kind of strange behavior. It's going down, and then in fact going to the minus infinite, and then comes back plus infinite, comes down here. It's basically actually discontinuous. Why that happens? Because for some actually initial value condition P naught, this denominator, basically this B part, this denominator may take the value of 0, may become 0. So something divided by 0, that's actually going to shoot up to infinity. And setting this in the denominator 0, we can find when that happens. And then so denominator may become 0 at this time. And I computed it this way, okay? So this is really bad situation. Once this happens, it's basically discontinuous, and then P goes to infinity. That means that the Kalman gain becomes actually blows up infinite. So that's not actually a right Kalman filter. So we must select the initial value, initial condition PT, and the right range. In this particular example, PT values larger than this particular limit. This is basically the negative solutions, which we abandoned, the negative solutions to the algebraic Riccati equation. Well, actually, this particular value varies depending on the many factors. But it is known that Riccati differential equations has the good acceptable solutions if the following conditions are met. if first of all, the system must be observable, F and H must be observable pair. And actually you pick the initial condition P naught to be positive definite and symmetric, positive definite, okay? Then hereafter, Riccati differential equations has solutions that's actually all the way positive definite and symmetric. And then that is usable for Kalman gain. And then more importantly, that the positive definite, the symmetric solution is unique. And then that's only the solution that we can use. So this is actually more theoretical ones, but all this analysis are coming from that matrix fraction decomposition, the technique we used to convert the original Riccati differential equation to a linear differential equations. That's a tool. Okay, now let's work out just a few examples. So first example is just a simple one. We deal with the scalar case, just one scalar variables for the state, and then actually process noise W, and actually quotient is just one, so very simple. Output side too is just very scalar, and process noise it's actually mean 0, and actually covariance is basically the 30 in the scalar case, and then this one the 20. Okay, whatever. First question: obtain the Riccati differential equations associated with the continuous time Kalman filter for this system, and solve it for the steady state value PT. Basically, going to algebraic Riccati equations. Okay. So first question, and the second question is the Riccati differential equations, and we use the fraction matrix, not matrix in this case, fraction decomposition method, and then convert the Riccati differential equation into using this transform to get the solvable equations. So first of all, yeah, plug in all the given parameter values, F and H and R, we can get this equation, which is actually a second order one, right? Even this is actually, it looks simple, but I know P dot and we have P square is involved. So this is actually nonlinear differential equations. So that's harder to solve. So let's look at the situations where that's in steady state. To set this one 0, and this is the algebraic different Riccati equations, and this one we can solve it explicitly, and then plug in the parameter values. It becomes this. That's simple. Okay, now the next one is to formulate the Hamiltonian matrix, and then solve that linear differential equations, right? So I know this one, plug in the Q and the R, that we get this expressions, and then eigenvalues computed this way, and then PD can be given by this. And just for sanitary check, pushing this one to infinity, we get this expression for P infinite. That's actually the same one as the previous one. So this is just a simple example, just a sanitary check. However, next question, I don't know how many minutes we have, but this example 2 is more interesting. And this is to demonstrate how flexible that the Kalman filter is. And in fact, this is to demonstrate that the Kalman filter can be used not only for state estimation, but also for parameter estimation, and combine the state and the parameter estimation. That's a key part of this problem. So again, the process state equations and output equations, just a scalar case, very simple. Okay, now we have A xt plus WT and C xt plus BT for Y. Okay, A and C are known constants. Okay, these two are given, known. And then WT and BT are respectively uncorrelated process noise and the measurement noise with the 0 mean value and variance Q and R. However, the tricky thing is that the sensor we use for measuring the output YT is not really actually, easy to use. It tends to have some bias B or drift or something bias B. So if you do the calibration many times and then do it well, that's fine. But I know in some situations it's not easy to do so. And like, let's see, strain gauge sensors, strain versus actually, strain is very much, dependent on the temperature and so forth. So sometimes very difficult. So let's see, some bias is involved. Measurement includes some unknown bias, okay, which is assumed to be constant, but it's unknown. So what we'd like to do is to build the Kalman filter to estimate both state variable xt and the unknown bias b simultaneously, okay, by using an augmented state vector. Then you scratch your head, what is this guy? Augmented state vector. Never heard of it. Yeah, that's true. However, this is something, the application of Kalman filter, okay? So as shown here, the output y versus the true x, you get the kind of linear relationship like this, but it's basically shifted from the zero origin. So this is bias b. Okay, we know this. We don't know this bias b. We like to estimate this. So let's extend the state variables, not only the original independent state variables, but also unknown parameter. We treat this one as yet another state variables. And we extend the dimension to a two-dimensional state space. Okay, so how it works? So, questions 1 is obtain the revised state equations and the measurement equation associated with the augmented state xt. And then we obtain the Riccati differential equations and then solve it for first, steady state. Okay, let's look at that first. So here's the thing. So bias is on the sensor. Therefore, the output function alone must be modified to, we represent that, together with the bias explicitly written, with yet another state variable b, right? So the state of transition is basically remain the same. X dot equal x plus wt. That's the original equation. That's fine. However, we augmented the state, and then we treat the bias b as a new state, right? So state equation should include the transitions of b. Okay, so that's actually dB dt must be added to that. But we assumed b to be constant, yet unknown, but constant. So that said that the b dot t is 0. It doesn't change. Therefore, the state equation in augmented space can be written this way. First, actually, this equation, so first line, xt equal this times this, so axt plus wt, right? But state space has been extended to x and b, so it has to be in this form, okay? Second line, b dot equals 0, dbt, 0, 0, 0, and then 0 wt. It is conceivable that the parameters is not actually perturbed by the process noise, right? So it is actually 0 over here, okay? So, that's actually a state equations in augmented space. Now, how about the measurement side? Measurement equations. And yt is actually usually cxt plus vt, but we have a bias b, right? So, we add the b to output the yt, measure the output yt. So you can actually, replace your original measurement equation by this expression, where we have state variables xt and the new state variable bt altogether. And then combining this, we can write it this way. So this is actually augmented the state, xt bt. To create this expression, you just form this vector or matrix, C times xt plus bt can be created. So this is our new H matrix. This is our F matrix, and this one the G matrix, the G vector, as such. Okay. So now question B: obtain the Riccati differential equation associated with this Kalman filter in an augmented space, right? And then first, the steady state value is to be obtained. Okay, so remember that this is the state equations, and this is actually a measurement equation in the augmented space, right? So from here, this particular part is matrix F. This is G, and then this one is actually H. So written here. Now this one is actually two-dimensional space. So P matrix is 2 by 2. It's no longer a scalar quantity. It is actually 2 by 2 matrix. So we need to form this Riccati differential equation, dpt dt such and such. And here P is actually again the 2 by 2 matrix, right? And the other terms that we need to formulate by using these actually FGH. So first, F times P over here is FP is given by this, and FP transpose, it's actually transpose of this guy. And then formulating this, so let's start with the P and times H transpose. H transpose is basically H is this, sitting here in the C1, and that is to create this vector. And then sandwiching that one from both sides together with the R, that part becomes this. This is actually this part, okay? And represented this way. So putting all together, we have this actually 2 by 2 matrix differential equations. So remember that's actually P is written this way. P1, 2, 3, 3 elements involved. Do you know why the P4 is not involved? Because P is symmetric matrix, so we have only 3 independent elements, P1, 2, 3. That's good enough. Okay, first FP, and then PF transpose is actually combined to get this terms, and this lengthy terms sitting here together with the Q. That's actually the last term. Okay, so this is the Riccati differential equations. Now, this is actually 2 by 2 matrix. So you can actually, extract 3 independent differential, 3 equations coming out of it. So dp1 dt, you pick this term and then this term and as such, right? P2 dt is actually this term, these terms must be corrected. Now, in the case of algebraic Riccati equations, we set the left-hand side to 0. So, from left top, 0 equals 0, this plus, and that one, that result in equation 1. And, this P3 terms, dp3 dt is also 0. 0 equal this plus this plus that actually gives this guy, and then 2 by 2 two elements here is also given by this. So you end up with 3 simultaneous algebraic equations with the 3 unknowns, P1, 2, 3. Now let's solve this. Starting from here, it's easy actually. This square is 0, so this as a whole must be 0. Otherwise, no solutions, right? So if this guy is 0, this one's also 0. So this all 0. So P3 must be 0. If P3 is 0, then P2 must be 0. So we determine P2 and P3 both are 0, right? So that result is substituted into this. So the remaining part is only P1. P1 turns out to be this equation. So solving this, we get the solution to this. So this is P1. we of course took the positive part. So P, infinite steady state, the 2 by 2 matrix, shown like this, and this is the result. So let's actually interpret this result. So question number C is that to discuss whether the bias can be estimated correctly, and under which conditions the state estimation error converges to 0. Obtain properties of the system and the parameter values that allow PT to converge to 0. Okay, so that's the question. So first of all, we end up with this and the steady state, covariance matrix 2 by 2, right? And remember that this component is P1, and then this one is P2, and then this component is P3. So looking at the P3 is associated with the B, that's actually second state variables, right? And then P3 is 0 at the steady state. The estimation of the sensor bias B converges to the correct value, the 0 estimation error, regardless of other parameters. Okay, it's going to 0. Okay, that's a very strong point. Note that this is possible because no process noise is involved in the bias dynamics. Remember that actually it's a parameter, so no process noise comes in. The estimation error of state xt becomes 0, P1 becomes 0, this part becomes 0, when either of the following the two conditions is met. Actually, from here, one is actually 0 sensor noise, R is 0, but actually that's actually not the feasible. But I know if R is extremely small, that's good. No process noise Q equals 0, and the system is stable or marginally stable. A is actually negative or 0. So this is the case we discussed some time ago. Scalar case we discussed, and under what the conditions it converges to 0 or not. The same argument can be made here. So that's all we can say about this. So what I like to emphasize here is that the Kalman filter is very flexible. So I know we basically use both state estimation and parameter estimation. We can integrate it, and we can expand the state space, treating those unknown parameters, and assuming that they are constant. We can do this kind of a treatment. So that is the interesting part. Well, today's lectures, we basically disrupted by the internet shutdown in my areas. I actually installed the backup generating systems to prepare for this situation. But Xfinity's internet service company, they did a poor job, so it was shut down. So I'm sorry for it, and I can't actually talk to you directly. So, but I know this video can be useful things for you. Yeah, that's it. Yeah. Bye.